Pluto is a distant and mysterious dwarf planet that used to be a member of our solar system's family of planets. However, surprise announcements by Neil deGrasse Tyson and Michio Kaku thrust Pluto into the spotlight with a shocking revelation. It shows that this icy world is on a collision course with Neptune. But how does it happen, and what are the consequences of such a great event? Are we witnessing a rare astronomical phenomenon, or is there more to this impending cosmic collision? Join us as we explore the possibilities of a collision between Pluto and Neptune, a former planet that was downgraded to a dwarf planet in part because of its unusual orbit. Pluto remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's orbit is close to that of Neptune. Tyson and Kaku expressed concern about a catastrophic collision between the two planets that would cause the Earth to suffer. How can such an arrangement be made? Pluto's journey around the Sun is unlike any other planet in the solar system. It took 248 years to make a full orbit, meaning there hasn't been a complete revolution since its discovery in 1930. But this idea doesn't stop there. Pluto's orbit is very spherical, deviating from the orbits of the main planets. The inclination is very unusual. Pluto's orbit is at an angle of 17 degrees to the plane of the ecliptic, which is higher than the orbits of the other planets. Along with its elliptical orbit, this feature adds layers of complexity to the model point. One of the most interesting aspects of Pluto's orbit is its connection to Neptune's orbit. About 20 years per orbit, Pluto moves closer to the Sun than Neptune, which defies what we might expect based on their position in the solar system. A natural question arises: why doesn't Pluto collide with Neptune? The answer lies in the planetary effects of other planets. The study of Pluto's orbit began shortly after its discovery, and at first astronomers struggled to understand its unique orbit. Unlike the other planets, whose orbits are very close to the plane of the ecliptic, Pluto's rapid ascent and elliptical orbit are notable. This mystery deepens when we realize that Pluto's orbit crosses Neptune's orbit. The stability of Pluto's orbit in these problems shows the complexity of space engines. The three-body problem in space explains how the magnetic field between three celestial bodies, such as Pluto, Neptune, and the Sun, depends on their moving. In the case of Pluto, this problem reflects the interaction of its orbit, that of Neptune, and the influence of the Sun. The terms apse angle library and latitude lift and VZK oscillation are the keys to this puzzle. Astrologers have determined that these factors help keep Pluto and Neptune at by, maintaining an apsis angle when Pluto crosses Neptune's orbit. The two planets will be at least 90 degrees apart in orbit and will not meet. Latitude refers to the vertical movement of celestial bodies in their orbits. In the case of Pluto, it means that when it approaches Neptune or another large planet and crosses it on their orbital plane, it has another layer of protection. The VZK oscillation, named after the scientists von Sippel, Kozai, and Litov, shows the consistency of Pluto's orbit despite its chaotic nature. These gravitational interactions help maintain Pluto's orbit and prevent it from colliding with Neptune. Without them, Pluto's orbit would become unstable, causing chaos in the solar system. In the late 1980s, annual simulations showed that Pluto's orbit is geomorphic, meaning that even small deviations from its initial conditions can cause large changes in the million years. However, these unique aspects of Pluto's orbit have been shown to maintain stability and control chaos over the long term. Recent computer simulations have helped scientists understand how the pull of Neptune, Jupiter, and Saturn work together to keep Pluto in orbit. These three giants act as guardians, ensuring that Pluto stays on its predicted path for billions of years. But what if this balance is disturbed? Could a collision between Pluto and Neptune be possible? Astronomers such as Michio Kaku have raised questions about the extent of the event's effects. The collision of two planets could offer a unique opportunity to observe extreme conditions in our solar system, which might even connect to advanced theoretical physics, such as string theory. String theory is a theoretical framework that replaces point-like particles with one-dimensional strings to describe fundamental forces in matter. A massive collision between Pluto and Neptune could create extreme conditions of energy and gravity, potentially making observable some of the effects predicted by string theory. For instance, the gravitational waves produced by such a collision might provide valuable data that could test string theory's predictions about gravity and spacetime, while the direct impact of a Pluto-Neptune collision on Earth would likely be negligible due to the vast distance. the scientific insights from such an event could be profound. Collisions allow us to test and refine our understanding of the fundamental nature of the universe. From particle physics to the nature of energy, Pluto's orbit is symbolic of the dynamic forces that govern the solar system. While the odds of a collision with Neptune are slim, Pluto's chaotic and unpredictable path is a stark reminder of how little we know about the expanding universe. Even with the most advanced computer models, predicting global events like this is challenging and uncertain. Finally, Pluto's spectacular journey around the Sun is a lesson in celestial mechanics, where coexistence and chaos exist. The relationships of passion between Pluto, Neptune, and other giants in the solar system show the balance of the universe. While the Pluto-Neptune clash will capture our imaginations, it also shows the importance of learning and observing. It reminds us that space is not static, but constantly changing and dynamic. The images transition from a wide view of the solar system to a more focused animation showing Pluto's orbit around the Sun and showing its interaction with Neptune's orbit. Audiences will witness the intricate balance of ancient art that has evolved over millions of years. As Pluto approaches Neptune, the camera zooms in on Pluto, showing that their orbits overlap but never cross. Author, voice. Despite these close encounters, Pluto and Neptune did not make it. This is because of the nature of the world created by the forces that control the world. Energy and time. Cut to a scientific video demonstration of the PSD angle library and latitude library mentioned earlier. The camera slowly pans over diagrams of orbital paths and gravitational vectors. Narrator, voiceover. Pluto's avoidance of Neptune isn't mere coincidence. It's the result of apse angle and latitude libration, mathematical phenomena that ensure Pluto remains safely distanced from Neptune, despite crossing its orbital plane. The animation shows Pluto and Neptune as glowing orbs on an invisible grid of gravitational forces, where waves of energy ripple around them, representing the VZK oscillation. Narrator, voiceover. The VZK oscillation, a critical factor in preventing chaos, maintains a delicate gravitational balance. Together, these interactions act like an invisible cosmic barrier, keeping Pluto and Neptune safe from one another. Transition to Michio Kaku and Neil deGrasse Tyson, who are both being interviewed separately in a split-screen format. A deep space backdrop is behind them. Michio Kaku on the left. The universe is full of these delicate balances. If even a slight perturbation were to occur, the consequences could be catastrophic. Planets can be thrown out of orbit or collide, creating a celestial event that can change the entire solar system. Neil deGrasse Tyson, right? Instead of as it stands, Pluto and Neptune are safe from such problems. The laws of physics have guaranteed that, for the foreseeable future, the two celestial bodies will remain in their cosmic dance, avoiding collisions at low frequencies. To make reasonable assumptions about what might happen may be fake or an external force that upsets this delicate balance. But what if unexpected things happen? What do you eat? Scientists have pondered the question. Could a rogue asteroid or an unexpected gravitational force throw Pluto's orbit into disarray, leading to an inevitable collision with Neptune? The animation shows Pluto spiraling closer toward Neptune, breaking free of its lib-rational safeguards. The two planets are shown on a catastrophic collision course. Narrator, voiceover. If such an event were to occur, the consequences could be catastrophic, not only for Neptune and Pluto but for the entire solar system. The moment of collision plays out in dramatic slow motion, showing the collision between Pluto and Neptune. The planets break apart, sending debris flying in all directions. The visuals expand to show the rippling effects across the solar system. Narrator, voiceover. The gravitational shockwaves could alter the orbits of other celestial bodies, sending debris careening through space. Planets, moons, and even distant asteroids could be affected. While Earth would likely remain physically unharmed, the cosmic ripple effects of such a collision would be felt throughout the solar system. The screen shifts to a view of Earth from space. The blue marble hangs against the backdrop of the stars as the narrator speaks. Narrator, voiceover. Earth, safely nestled within the inner solar system, would remain largely unaffected by this distant event. However, the explosion of scientific knowledge that would result from such a collision would be groundbreaking. Transition to an animated visual of gravitational waves and cosmic energy emanating from the Pluto-Neptune collision, traveling through space toward Earth. Narrator voiceover, gravitational waves, detected here on Earth, would provide invaluable data for scientists, offering new insights into the nature of space-time, gravity, and even string theory. Cut back to Neil deGrasse Tyson, who speaks directly to the camera. Neil deGrasse Tyson, the idea of a planetary collision sounds catastrophic, and it would be, but it would also provide an unprecedented opportunity for us to study the universe. Events like this would stretch our understanding of physics in ways we can't even imagine yet. Transition to Michio Kaku, who smiles as he explains. Michio Kaku, and who knows? This event may reveal the new trends predicted by string theory. This is the kind of event that theoretical physicists dream about even from a safe distance. Neptune continues its orbital dance. It's quiet,